Hello, another live stream Calypso. We're getting started a few minutes early. We'll dive right in as soon as everyone is here. I'm trying out a new microphone, so let me know if it's a little bit too quiet, a little bit too loud, or if I should switch back to what I had. Go ahead and share my screen. Sorry for the delay. I started the stream a couple minutes early. I just want to make sure everyone is available to start. We will start in just a minute. All right, it's close enough to 11 o'clock. So let's dive right in. Today, the topic is composite position. We're going to look at an example like this one right here, where we have a true position applied to a pattern of holes. There's 20 thousandths tolerance to E, F, and R, and a 7 thousandths to E. And we're going to look at how do we apply this in Calypso. So here we have the same part with a pattern of 6 holes. And this program is already done, so I can walk through what I have here, and then we'll start from scratch. So we'll move down our characteristics list here. So here we have two different position callouts. We'll go back to our drawing here, 53 and 54. So you do need to separate it as two separate characteristics. And then back in here, I have these features programmed as a pattern. You can do them individually or a pattern, either way. And there's a couple approaches to this as far as applying the datum reference frame. You can create a secondary alignment, or you can input the datums directly here. So we have plane E, and then datum F, which is our cylinder, and then datum R, which is the symmetry point on that slot. So it accomplishes the same thing that I had before, or almost the same thing. There are some slight differences on how you can control the datums. But as far as understanding or interpreting that composite callout, we have to understand that the top callout is controlling the location and orientation of all the features to all those datums. The second callout, the second tolerance, is only controlling the spacing and orientation. So it's like it's floating within that zone. So we go back to here. This first callout with the 20 thousandths is pretty much the same as any other true position. But the second one with less datums, what that is telling us is we don't need to control the spacing of the pattern as with a larger tolerance. It has a tighter tolerance, actually. So in terms of function of this part, what's more important is the spacing of those bolt holes. And notice the second tolerance is not controlling the rotation to that slot. So let's go ahead and check out what we have for this. So there's another function in Calypso for a bore pattern. So if I create a position in here, there's two options up here. There's the regular position tolerance of an individual feature, or you can do a bore pattern, which allows you to control best fitting. So in here, we can select the elements or the features. We're going with those threaded holes. And it's asking, do you want to cancel the pattern? In other words, do you want to expand the pattern? And down here, we can control whether rotation or translation is part of that calculation. In this case, the position is on the bottom. We don't care about rotation necessarily. All we care about is the spacing of the pattern. So we can let it float. So here we have these two. We can uncheck actually all of these and allow it. No, sorry. We do want them checked. So when it's checked, it means it's allowing the fitting. If you uncheck, that causes a restraint. So now we can put the primary datum as datum E. Put our tolerance in here. And we're putting the tolerance on all the features. So click yes. So again, the first characteristic is going to be like a regular position callout, applying to all the features. The second characteristic is going to be a best fit with fewer datum references because we're only controlling spacing and orientation. And this would work for other types of patterns. If it's not a circular pattern, maybe it's these four holes. But regardless of the orientation of the pattern, you still would have two separate callouts. On some composite position, you might have three different callouts. So you might have three datums on top, two datums on the second one, and one or none on the last one. So each segment is a refinement of the one above. So I hope that clarifies a little bit of how to do composite position, because each one can be slightly different, and you have to interpret the datums based on what features they are. So in here, datum EFR, we have to look at the whole drawing. Datum F is a cylinder. Datum E is a plane. Datum R is the center of the slot. And these are interpreted in order from left to right. So the plane comes first, that's your leveling. The F, the cylinder, comes second, so that's your origin. And then R, which is the slot, controls the clocking. The second callout with only one datum, the plane, and since it's applied to a pattern, we know that it's only controlling the spacing of the pattern without reference to the center bore and without reference to the clocking. So I'm going to just do a little quick illustration here. I like to explain this concept to those of you who are new to composite position. It's just a little analogy. So imagine you're hiring a contractor to install a fire pit in your yard. So you have your house. Let's see if we can get this to look better here. Okay, so this is really a barbaric drawing, but so you have your house and then you have your yard. Let's say you have a fence and you want to have a fire pit in the backyard, let's say 100 feet from the west side and 20 feet from the north side, plus or minus 10 feet or so. It's not super important where that fire pit is in relation to your property. So then the contractors, they install the stones, they create this pattern of stones in a circle. And this reminds me of a bolt circle. Now, what is more important to you is the diameter of that fire pit and the spacing of those stones. The rotational alignment doesn't matter at all. So think of it when we're looking at this composite position, the top tolerance is the location of the entire pattern relative to the rest of the part, or the less critical features. The lower segment is a tighter tolerance, controlling what matters more in the assembly. And the reason we do this is to actually save money, because if you put the 7,000s tolerance on everything for location, orientation, spacing, that would be more difficult, more expensive to manufacture. So we're allowing more tolerance on the things that matter less. Okay. All right. So that's composite in a nutshell. You can do the features as a pattern like I did here as far as programming them, or you can put them in separate. The advantage of doing it as a pattern is just quicker, but there is a disadvantage. You don't get to see every result in your program right away, but they will show up in the report. That's why you have this, says 1, 6, 1. It means it's a pattern with 6 features. So let's open it up to questions. If you guys have any questions in the chat. People are quiet today. I know it's a busy time of year. Another thing you can do as far as alignment goes, you can do a 3D best fit, and sometimes that helps giving you more control. So if I go to Resources, Utilities, 3D best fit, I can select elements and then go to those circles. And down in the best fit, we can control which way we're best fitting. So if we want to satisfy this callout, we're allowing shifting because the datum F cylinder is not there. We're allowing rotation because the datum R slot is not there either. So we're going to allow it to best fit XY, not Z, and we're going to allow it to rotate around Z. So if these 6 holes are shifted to the right or twisted clockwise, the best fit is going to correct that. And this is effectively doing the same thing that we did here. Sometimes I prefer to use secondary alignments because they can give you a little bit more fine-tuning control on which datums are doing what. All right, so there aren't any questions in the chat yet. So let's go ahead and talk about these threaded holes. So you'll notice we have these, each of these holes are being measured with a spiral or helix scan. Turn off actuals. There's a couple different ways of checking threads. You can do it with a spiral scan like this. You can do it with linear scans. You can do it with true position inserts or locators. So to do a spiral scan, you would put in a helix path. And I typically like to do 2 rotations at least. Then you would put in the pitch of your thread. So in metric, if it says M2 by 0.5, the 0.5 would be a pitch. If it's an inches thread, like a number 4-32, the pitch here would be 1 divided by 32. So you put that in here, give it a reasonable speed and point spacing. You want a couple hundred points at least. And then make sure you have your filter and outlier turned on. And you're good to go. So that's effectively getting the center point of that hole from the minor diameter. It's a little bit better to do it off of a locating gauge because that's getting off of the pitch diameter. Okay. So we covered composite position. We looked at some thread stuff. We do have some other questions that came in from last time. One of them was using multiple datums. I'll have to think if I can come up with an example of that here. So the question was, how do you handle multiple feature datums? Like if you have a shaft, two different cylinders where they're both called out A-B or something like that. We could simulate that here. Let's say this bore, we've got two different cylinders. Again, in Calypso, there's a couple ways of doing the same thing. We can do this with a circle here and a circle here. So two different circles at the opposite ends. And then we can create a 3D line. Go to Options, Recall. And take the two circles. Okay. And now we have a line through that. So we could use that 3D line as our datum A-B. Another way is you would have two separate cylinders. So you have 3D features, and then you can do a 3D line between the cylinders. That line you'll notice is a little bit shorter because it's going to the centroid of each cylinder. But Calypso also has a feature called a stepped cylinder. So we can go to Features, Special Geometries, and Step Cylinder. Notice it's going to be theoretical right away. This is not something you measure directly. You have to measure the two cylinders separately. So then we go recall feature points. Cylinder 1, cylinder 2 with the control key. And it's flashing on me. So we have the step cylinder, and it will give you two different diameters to report. So notice now we have this tab for the diameter and for the positions. So diameter 1, diameter 2. Diameter 1 is the bigger one, 2 is a smaller one. So the nice thing about this is it considers it as one feature, and it will allow the calculation of it all together. So let's say we did a circle on this outside diameter, and then we do a position. Circle 4 back to the step cylinder. Notice on the step cylinder now we can apply MMC. And we do need to create the characteristics or the diameters that go with that. So it's kind of a rare case you'll see a combined datum with MMC applied to both. but you can do that. So in the diameter characteristic for the step cylinder, you can have the output of both. You put the separate tolerances for each. All right. So the same would apply for an outside diameter, like a shaft. You'd have two separate diameters, two separate features. You can just put a 3D line through it or create a combined cylinder from both, and that becomes your datum. Okay, Vishal says, how do we call out the position of the slot at MMC? All right. There are two examples of slots. We've got one here. We've got one over here. So slots are a little bit tricky because they're not like a diameter. But this does happen from time to time where you see a slot called out for position, and it might even say boundary. So what that means is this slot has an imaginary boundary at virtual condition or worst case size and location that it cannot penetrate. So Calypso cannot do that complex calculation exactly, like a slot at MMC and everything, but you can approximate it by doing two separate position callouts. And oftentimes the slot position will have location called out with a larger tolerance in the long direction and a smaller tolerance in the short direction. So let's just show some examples here. So if I wanted to do them separate, I could do a symmetry point, taking two opposing points, and get the position of that symmetry point in the y direction only. So make sure you pick that. And then right here we can choose MMC. Make sure you have the slot width being reported as the symmetry width. And we would put in whatever tolerance you have. So that's how we report just the y direction with MMC. And then the other direction, it's a little bit more steps here, but we can do a circle on either end. Then we'll get a symmetry between the two. That's our midpoint in the x direction. So then I do another position of that symmetry in the x direction only. The only problem here is we can't do MMC directly. We can't report that. However, we can use a formula. So I'm going to put in a caliper distance across the length of the slot. So from circle 5 to circle 6, we're using the maximum distance in x. So then in our position tolerance, we can go here, right-click formula. We'll put in what we have to start with for tolerance, plus, then we take the Cartesian distance, actual. So we want our bonus tolerance will be the difference between the the MMC size and the actual. So we have to go check what that is. So this is 996. Let's say it's plus or minus 10 thousandths. So MMC would be 0.986. So we have our 5 thousandths plus the actual minus 0.986. When you put these formulas in, you have to use the 0 before the decimal. So this will calculate the total available tolerance, including bonus. So that's how I typically handle slots. You can measure a slot as a slot feature by taking points and creating the slot all the way around. But when you go and report the position, it's going to look a little different. Let's bring this down here. So you can do a diametrical zone XY, but that wouldn't really apply with a slot. You can do, though, a rectangular XY and give yourself tolerance in X and Y. This might be the most condensed way of doing this because you can, let's say you have 10 thousandths in the X, 5 thousandths in the Y, and then you could put your formulas in there to include any bonus tolerance. All right. Next question. Rohit says, can we calculate the position directly without taking any alignment? I would say the answer is no, because a true position implies that you have some type of reference. You need to locate the position relative to something. So if I take a circle and there's no alignment, there's no way of telling where it is. However, sometimes, though, you see weird cases where there's a position tolerance with no datums after it. And what that is saying is there's no orientation or location references. Typically, it's applied to a pattern of features. So it's controlling just the spacing of those features or the relationship of one to the other. So we could possibly see a position call out to a bunch of cylinders, and then there's no datum. And that would mean it's just relative to each other as a best fit. So in that case, I would use resources, utilities, geometry best fit. And again, you can do the evaluation constraints in whichever directions are needed. But in this case, if there's no datum references, it just says position with a tolerance, then you would leave all these checked. So like I said, in this example, there could potentially be another tolerance below that says maybe 0.003 with nothing, with no datums. And the way that we would interpret that is this one is controlling the spacing of the pattern and perpendicularity to the plane. And then the one without a datum is controlling just the spacing of the features to themselves without regard to the plane. So it could possibly best fit and twist. All right, we have a few minutes left. Any other questions from you guys or possible suggestions for next time? I know there was a question about profile. We can definitely dive into that. That's a common challenge. Kidan, or Kidane is asking, can you make a video on how to measure pitch diameter of a thread? That is actually not possible in Calypso. You have to use a thread gauge because the pitch diameter is in the grooves of the thread, and your probe is not going to be small enough for that. Pitch diameter is somewhat halfway between minimum or the minor and major diameter. It's actually the contact point where the mating part would touch as it's threading. All right. Thanks, guys. Again, we will take it up again next week. I look forward to your suggestions and have a great day.